Hey guys, this is Bill. Welcome to my channel. In this video, I'm going to introduce you to the concept of cross-validation. If you are new to machine learning, you may find this video a little abstract, but don't worry about it. It's perfectly normal. Just watch the video until the end and take note along the way. If you need it, you can download the slides in the description link below and revise the concept. After a few times of revision, I'm sure you can master the concept of cross-validation. Cross-validation is a technique that we use to determine a good tuning parameter value. Since tuning parameter is user-defined, the choice of it can often make or break the model. For example, in the LASSO and ridge regression, lambda is considered a tuning parameter, which is user-defined. As shown in my previous video on how to do a lasso and ridge regression in R. While some lambda values help improve lasso and ridge regression models' ability to predict out of sample, other values of lambda seriously hinder the performance of lasso and ridge regression. Hence, it is critical for us to use cross-validation to pick a good lambda value for lasso and ridge regression. If you are somewhat familiar with machine learning, you should have heard the term training data and test data, or train set and test set. We feed training data in a model and get an estimate for the coefficients, and then use the estimated coefficients and the independent variables or the x variables in the test data to predict for all the observations in the test data. We compare these predictions with the real response variables or the real y values in the test data. Computing the sum of squares of residuals, or SSR in short, help us determine how good is the model's ability to predict. Now, back to use cross-validation to find a good value for tuning parameter. Let's use lasso as an example, and the tuning parameter is lambda. In order to determine a good value for lambda, we should carry out a cross-validation with only the training data. First, let me use a concrete example to show you how cross-validation is done with a train set. Let's say we divide a train set into 4 folds, and then we feed the first 3 folds into a model. Let's say the model is lasso with lambda equals to 0.2. Then we obtain a set of estimated coefficients. We use the estimated coefficients and the independent variables in the 4th fold to predict the y variable for the 4th fold, and we compare the predicted y with the real y values in the 4th fold. Get an SSR, we call it SSR1. Here, we call the first 3 folds pseudo-train set and the 4th fold pseudo-test set. We then repeat the step with the 3rd fold as the pseudo-test set and the rest of the 3 folds as pseudo-train set, and get SSR2. And then we do it with 2nd fold as the pseudo-test set. And lastly, we do it with the 1st fold as the pseudo-test set. Eventually, we get 4 SSRs. Sum them up, and we use that sum to measure how good the model lasso with lambda equals to 0.2 performs out of sample. We then repeat this whole process with different lambda values for the lasso model. Let's say we try it with lambda values equals to 0.1, 0.2, 0.3, all the way to 1. Then we should get 10 SSRs for the 10 lambda values. We pick the lambda value corresponding to the lowest SSR. Then, with the chosen lambda value, we feed the whole train set and get a set of estimated coefficients. And that's it. You are done with cross-validation. Now, let's do a quick recap. First, divide your train set into k folds and pick a fixed lambda value. Let's call it lambda 1. Then, use the first fold as pseudo-test set. The remaining k-1 folds are the pseudo-train set. With lambda 1 and the pseudo-train set, you get the estimated coefficients. With estimated coefficients and x variables in the pseudo-test set, you predict y for the pseudo-test set. With predicted y and the real y values in the pseudo-test set, you can compute SSR. Repeat the process with different pseudo-test set. Then you will get k SSRs. Sum them up and use it as a measure on how well the model predicts out of sample. Then repeat this process with different lambda values. In the end, pick the lambda values with the lowest SSR and fit the whole train set with the chosen lambda.